In this recording, we'll discuss circuits that are made up of resistors or light bulbs in parallel. Okay, what makes a configuration parallel is when the two elements, light bulbs in this case, having both ends touching. For example, you see this end of this light bulb is touching this end, and then the other end is also touching the other end. Both ends of both elements have to be touching for both elements to be in parallel. Now, these two elements are in parallel with a battery that's feeding the current. Now, let's think of it like we thought of the other one. Let's start with two wires, one with a diameter D1 and the other diameter D2. So they are different cross-sectional areas. They have the same length. This one has a resistance R1, this one has a resistance R2. Putting them in parallel is equivalent to combining both of them, having a thicker wire with another diameter such that the area here is equal to A1 plus A2. Now, what's the resistance of this one? Using the formula for resistance, it's rho L over A1 plus A2. Knowing that the resistance of this one is rho L over A2 and the resistance of this one is rho L over A1. Now, notice the relationship. How can we find a relationship between these? If we invert both of them, 1 over R1 is equal A1 over rho L. What's 1 over R2? 1 over R2 is A2 over rho L. What's 1 over R equivalent? Is A1 plus A2 over rho L. So you notice from there that I can find this by just adding these two. In other words, 1 over R equivalent is equal to 1 over R1 plus 1 over R2. If I had more than two resistors, if I had the third one, for example, it would be plus 1 over R3, fourth one plus 1 over R4, and so on. Okay, so that's the idea. Why resistors in parallel? To find the equivalent resistance for resistors in parallel, we have to invert each one of them and add up the inverses, and then once we find the sum of the inverses, we invert that to find R equivalent. Notice also the equivalent resistance should be less than the individual resistors. It's essentially a highway with multiple lanes. A highway with multiple lanes has less resistance than either one of these since it has the same length. Okay, let's go to a simulation. So I have it made up here. I have two identical light bulbs and a third identical light bulb. All of them are subject to identical batteries. Now you notice here the light from this is very much the same as the light from this, which is the same as the light from this one. And that makes sense because if I take a voltmeter and measure the voltage across this, we should find 9 volts, the voltage of the battery, and that's what we found. Voltage across this, we should find the same thing, voltage across the battery. Voltage across this, 9 volts. And then in this case, all of them carry the same current since they are identical. 0.9 amps, 0.9 amps. This one here, 0.9 amps. What that means is they carry the same current, they are subject to the same voltage, so they are going to give off the same amount of light. However, when we compare this circuit to this circuit, of course, I'm getting more light because I have two light bulbs lighting up. So how much energy is being used from the battery in here compared to here? Of course, it is twice as much because I'm using that amount of energy here and that amount of energy here. And as a way to check that out, we can check the current coming out of the battery. And notice here it's 1.8 amps. The sum of this 1.9 plus this one. So actually the charges, when they come here, they find two paths, two highways. And since the paths have identical resistance, they are going to be equally divided among them. So that the overall current is going to be divided into 0.9 and 0.9. Once they meet back here, they are going to add up again, giving us the 1.8 amp again. Now, what kind of resistor should I use to replace these two 10 ohm resistors? Okay, they are 10 ohm resistors. To get the same power out of the battery. So instead of 10 ohm where I get half as much power, I'm going to have to use a smaller resistance. I'm going to go for 5 now. How do I get the 5? 1 over 10 plus 1 over 10. It's 2 over 10. So it's 1/5. And the inverse of 1/5 is 5. So this resistance should be 5 ohms. Okay, now when I have here 5 ohms, I have a current of 1.8 amps out of the battery. And the voltage is still 9 volts. And you notice this light bulb is now brighter than either one of these. It should be as bright as both of them combined. Okay. Now, a key to resistors in parallel, both ends are connected, and the current is split between the wires. Okay, we have seen that the voltage is the same across both of them. I'm going to do it for non-identical light bulbs. So I'm going to change this one to 20 ohms. Now when we have that one at 20 ohms, notice here it is not as bright as the other one. So the 20 ohm resistor right now, it's less bright than the 10 ohm resistor. That's opposite than what we saw when we had them in series. Now let's check the voltage. Voltage across this one is 9 volts. Voltage across this one is again 9 volts. The voltage should be the same, and that makes sense because remember I have a wire here that's connecting this end to this end, and that wire should be at the same voltage. And this wire here is also at the same voltage, same electrical potential. So each of the light bulbs, despite the fact that they are different, are subject to the same electrical potential difference. That's because both of their ends are touching. Now, what about the current flowing through each one of them? The first one, the same current we measured before. And we can get that through 9 volts divided by 10 ohms, 0.9 amps. The other one, it should be 9 volts over 20 ohms. It should be 0.45 amps, and that's exactly what we see. So when resistors are in parallel, voltages have to be the same, but the currents are not necessarily the same. We find the currents by using Ohm's law. The currents, we find them by using V is equal to Ri. The V's are the same, but the currents are not necessarily the same. They are only the same if the resistors are identical. Now, to find the equivalent resistance, let me calculate it here. So 1 over R equivalent is going to be 1 over 10 ohms plus 1 over 20 ohms. So in this case, I'm going to put them in the same denominator. So 2 over 20 ohms plus 1 over 20 ohms. So that gives me 3 over 20 ohms. So my R equivalent is the inverse of that. So R equivalent is 20 over 3 ohms, which is 6.67 ohms. Okay, let's try that out in the circuit. So I'm going to change the resistance here. 6.66667 ohms. Okay. Measure the voltage. It should be the same 9 volts. The current out of the battery, we want it to be the same as the current out of the battery here, 1.35 amps. Guess what? It's the same thing, 1.35 amps. Okay. So the sum of the currents is the equivalent current, but the voltage across each one of them is the same. Now, this is the example that I worked a little earlier. If we had 10 ohm, 1 over 10 plus 1 over 10 is 2 over 20. I mean 2 over 10, sorry, which is equal to 1 over 5. The inverse of that is 5 ohms. That's my equivalent resistance. Remember what happens as the current is flowing out of the battery. Once it meets the junction, the two different paths, it's going to divide among the paths. If they are identical light bulbs, it's going to divide equally. If they are different, it's going to divide according to the resistance. The lower resistance is going to have a higher current than the higher resistance. Essentially, think of it two highways. A multi-lane highway, that's the low resistance, and a two-lane highway, that's the high resistance. More cars, more currents, more current is going to be through the multi-lane highway. Now the question is, in here, how much would the current through the battery change if I unscrewed one of the two light bulbs if the light bulbs are identical? Of course, you see the current through the battery is going to be halved. We did that in the simulation a little while ago. When we had the simulation, we had 0.9 amps here, 0.9 amp here, and 1.8 through the battery. So when we remove one of the light bulbs, it's just 0.9 amps. Now, how would the brightness of one battery change if you unscrew another one? And let's go back to it. Instead of unscrewing, the simulation does not allow me that. So I'm going to split the junction here, paying attention to the brightness of that one. And you should notice there is no change. Put it back, no change. Now if they were in series, we didn't do this for series, but let's put this, let me try to remove this light bulb and put it in series. Okay, they are lit right now. Okay, let me make the battery stronger so we can see a little bit more light. Okay, they are both lit. The 10 ohm is less bright than the 20 ohm. And if we disconnect one of them, like having one of the light bulbs burn, and we don't have light anymore because the circuit is not complete anymore.